Everybody, it's Brad and Joseph, the two founders of Roboflow, and we're here for another fireside computer vision chat. Today we're talking about image augmentations, and so I'll let Joseph open it up with what is image augmentation and why do you need to apply it for computer vision models?
Hey everyone. So image augmentation is the act of actually deliberately almost dirtying up your training data to produce variation so that your model can learn a more general setting. So simply put, it's taking an image from your source training data and then applying some manipulation, maybe a brightness change, a flip, rotation, blurring, so that you can create additional examples for your model to learn from. Now, it's kind of confusing as to why you might want to deliberately mess with your training data. Like, why would you want to take an image and almost make it be lower quality? Like, why would you want to add blur or some of these other things? And I know you'll talk about specific cases where different augmentations make more sense, but the big picture reason that augmentation is valuable is you don't want your model to memorize your training data. Whatever images you capture are not going to be perfectly representative of the real world. You know, if you're in a real world setting and let's say you have a camera that's sitting by the highway and just counting cars that go by, there could be different times of day. It could be bright or dark. Maybe sometimes the camera is further away from the road, the way you set it up. All these sorts of considerations change what the setting looks like. And you could either try to collect data for all of those individual settings, or more realistically, you could collect some data, or as much as you can that's going to be representative, and then modify those images so that your model can learn not to memorize, when it's bright outside, that's when I happen to see more red cars. If just in theory, in your training data, a bunch of red cars went by when it's brighter outside. And so augmentation is really, really essential to making sure your model generalizes to more settings more effectively. In a sense, it's almost like creating more data. Now, augmentation isn't a cure-all, but it does help. And it's almost a no-risk option. There's no reason not to try it. But knowing which augmentations to use when is important, because not every augmentation is actually necessarily going to improve model performance. There might be times where an augmentation is a bad choice for a given setting. So I actually want to dive into that of maybe you could break down some different problem types, and I touched on some augmentations, but you could run us through what augmentations might we want to select based on those different problem types.
Sure. Yeah, I think that was a good overview of why you might want to apply augmentations. And I think one other thing that I would add to that is also that there's a cost consideration here too of course, you might want to go out and just collect more of those videos of cars driving by, but then you have to get those annotated and, it takes a lot longer to train the model. And so augmentations are kind of a essentially no cost way to expand the amount of data that you have. So I'll dive into that example that you gave of, you have your camera sitting on an overpass and you're counting the cars going by. What types of augmentations might you apply and why you can't just kind of naively apply the same set of augmentations to every image, every domain automatically. So if I was looking at that problem, I would be trying to think, if I'm going to put a camera on a different overpass somewhere else, what are the things that might be different about the images that I'm not actually necessarily capturing with the training data that I'm getting from my one overpass that has my camera? So the first thing I'd probably do in almost every case is do a horizontal flip, because it really doesn't matter whether the cars are on the left side of the frame or the right side of the frame. You really want to know, you want your model to work well on both.
What is horizontal flip?
So a horizontal flip, you can imagine it like looking in the mirror at a photo. So it flips it this way. And in a car situation, actually, this is something where if you were collecting your training data in the United States, you'd get all cars driving on the right side of the road, and then you'd go to deploy your model, and it might be confused about which direction the cars were driving because they drive on the opposite side of the road. So horizontal flip could be a good thing there. Or if you only are going to be collecting data in the United States or places where cars drive on the right side of the road, you might be thinking about is this actually going to represent my training data or my real life data when I'm doing inference, and maybe decide that a horizontal flip isn't the right thing to do. So that's one example of an augmentation that you could apply to this. running through some other things that I'd be thinking about are like, what is the orientation of the camera, right? Like maybe some overpasses are higher or lower, or the cars are closer or farther away from the camera. So I'd be thinking about doing potentially a crop, which is essentially a zoom, where you're taking a square of the big picture and training the model on just a subset of that. That's going to do two things. It's going to help with the zoom factor of like maybe the cars are closer or farther away, or maybe some cars are slightly bigger or smaller than other cars. The other thing that it's going to do is apply a little bit of occlusion. So if a car is near the edge of the screen, it's going to essentially crop out part of that car. And by doing that on all the different sides of the frame, you're going to teach your model not just to identify the whole car, but if there's two cars in a line and you can only see half of the car, if you've given your model enough examples where there's only half of the car shown, it's going to learn not just to identify a car as the front view of two wheels, a hood, and the top, but you also teach it like, oh, maybe if you only see the side view mirror, or only half of the car, or only the bottom part of the car, it's still going to learn like those different components of the car and learn multiple ways to identify a car. The other thing I'd be thinking about is rotation. So perhaps your camera is at a bit of an angle, and so on the horizontal axis, that would be a what we call in Roboflow a rotation. We also have perspective correction, which is essentially simulating rotation on the other two axes that your camera might be rotated. So you don't want it to be that your model is super sensitive to being exactly positioned correctly, dead on with the lane coming at you. You might want to make sure that you're building in some variety there. So those are some of the considerations. You touched on lighting. I'd probably do exposure and contrast adjustments, probably some hue adjustments too. Your camera in real life is going to auto pick its white balance, and so by adjusting the colors of the image, you'll account for some variety there. And also, cars come in all different colors, and so you don't want to be overfitting on just the cars that drove under your overpass. And maybe it is that you're collecting data in LA and those people are like more excited about red cars, and New York likes green cars. So you kind of want to just apply all that variety. So that's one example of like your car is on the overpass. Maybe you could touch on why you might not want to use those exact same augmentations if you're talking about a different domain. So like let's say you're collecting this car data from a drone or from a helicopter, and you're instead of counting the cars coming by, you're trying to like count them from the air. How would you change the augmentations for that use case versus a traditional camera sitting on an overpass?
Yeah, so I think it's a good question. So in other words, in one scenario, we have the camera in a fixed position over top of an overpass, and cars are going by. And in the other scenario, perhaps we have like our camera on a drone, and the drone's flying around, and maybe it's still looking at cars below. So yeah, I think some things that come to mind that are different about those scenarios is, in the case where we have the camera on the drone, we don't actually know which perspective the camera is going to be facing relative to the cars below. So in other words, you can envision that in addition to like small amounts of rotation that you mentioned of the camera being in a fixed position, and it might not be perfectly at a 0 degree, so maybe you want +5, -5, the drone could be at a full 90-degree different rotation almost in every direction. And so I'd recommend a 90-degree rotation as an augmentation technique that you could apply. Meaning you're going to take the image, you're going to fully potentially flip it on its side. Now that would look pretty nonsensical in the overpass use case, because it would look like your cars are now driving sideways, and that wouldn't make a lot of sense. But for the drone looking nadir to the ground, it really could be driving or flying at any different orientation. So that's one that like is a good compare and contrast in this circumstance. There are some that overlap in terms of like valuable ones. So you mentioned like crop, which would be taking a smaller subset of the image. Crop makes a lot of sense in the drone flying use case, because maybe the drone's flying at 100 feet, maybe sometimes it's flying at 300 feet. And models, as you mentioned, are very, they're smart but brittle. And so if they learn what a car looks like at 100 feet, they don't actually necessarily know what a car looks like at 300 feet, or vice versa. 300 feet doesn't look the same as 100 feet. So randomly zooming in on a part of the image and then passing that to the model allows the model to learn the different levels of perspective to what the image could look like. I think you touched on this, but the idea of occlusion could be really important. Occlusion meaning that something is blocking view of something else. So right now, my hand's occluding my face for the camera frame here. If we have the drone example, and the drone's flying over top of the road, maybe it's not always flying over well-cleared highways. Maybe sometimes it's flying over an area where there's trees that kind of shade and protect part of where the cars drive by, and they occlude view of the drone camera to the cars below. Then we would want to simulate this occlusion in our training data so that our model, again, just like you outlined in the case of partial cars on the edge of our frames, the partial cars could also be in the center of the frame if there's a tree blocking view. So there's an augmentation that's actually relatively new called Cutout, where it looks kind of funny. It adds black boxes on top of your images. And while that looks kind of funny to humans, to the model learns that the portions of the image that are not covered by the black box pixel are still the object itself. And with Cutout, you could randomly have large black boxes, maybe 1 per image, maybe 3 per image, to basically simulate different levels of occlusion that you might expect to be on those individual images. I think one thing that I do want to touch on as well is, in a sense, there's categories of augmentations that almost feel like color changes. Like you mentioned hue. We're not changing the perspective. We're just changing the colors in the image. Or brightness. And then there's perspective changes, where we're rotating and the perspective is different. Could you talk a little bit about what happens to our bounding boxes in both these circumstances? Because if we have an image and we 90-degree rotate it, and if our bounding boxes were still where they were originally, suddenly they don't make any sense. So how does that work with augmentation?
Yeah, of course. And actually, maybe we should take a step back and describe kind of what those bounding boxes are. We actually have another video that we'll link below about the different types of problems that you can solve with computer vision. And so Joseph just was mentioning bounding boxes. These come into play in an object detection model. So you can imagine if you're doing a classification model where you're just saying, like, are there cars in this image or not? You don't actually need to do anything else. You can just kind of transform the image and your model will learn image-wide details. But if you're doing an object detection model where you want to know not only are there cars in the image, but where in the image are those cars, all those transformations that you do on the pixel data, you also need to do on the annotations, which are metadata on top of that. And so, there's some trigonometry that you have to do with perspective corrections and with rotations. It actually gets a bit tricky because it's not just the position that needs to change, but also oftentimes the size of the bounding boxes will need to change as well. So you can imagine if you're rotating this way to still encapsulate that bounding box, the new bounding box needs to be a bit bigger. Otherwise, you're going to be cropping out portions of it. And if you crop an image, you're going to have to translate it around. And you can imagine as you stack all of these augmentations on top of each other, because you're not just going to do a rotate and a hue transformation, you're probably also going to apply a whole bunch of other transformations in sequence. The final image looks a lot different, and the annotations themselves are a lot different from the input. So that was a decent overview of the different types of augmentations and kind of how they, in theory, work. But in practice, let's say you've come up with your list of augmentations that you want to apply to an image. How do you actually go about doing that and feeding that into your machine learning model?
So process-wise, augmentation happens typically, exclusively, not always, but typically just to the training data set. And so we'll say you have, we'll make it easy, 100 images captured of the problem you want to solve. Maybe our car's above the highway. And we'll say we have 70 of those images in our training set, source images. We would want to augment that 70 by applying these series of transformations. This is something that we work on making easy with the Roboflow platform, of being able to select which augmentations are going to work best, and allow you to actually preview which of those augmentations and what they're going to look like on the data set. But in terms of the flow, you'll decide, okay, of these 70 images, I'm going to apply, to your recommendation, brightness change, zoom, maybe a random crop, maybe cutout for the occlusion problems, horizontal flip. So I'm going to decide that those augmentations make sense. And then I'm also going to be able to say, how many images do I want to create from my original 70? Because just as you mentioned, augmentation is a no-cost way to increase the size of your data set. And so maybe I want to create 5 versions of each of those input images. So I go from 70 to 350 of those output images without needing to collect any additional data. And so I would apply those steps, and then I have my training data. And from there, I would have my training, validation, test, and I'd go about actually selecting and training a model for my process going forward.
So I've got a question. I've been reading actually some of Jacob's blog posts about the augmentations that have been applied in some of the newer machine learning models as part of the training pipeline. Does that mean that I don't need to apply any augmentations to my data set? Is that just being handled for me by the model these days? Or are you seeing results when you're training by also applying augmentations beforehand?
Yeah, it's a really good question. So some models, some new architectures include augmentation as a part of the training pipelines, as you mentioned. Some other models do not. And there's no augmentation that happens during what's called train time augmentation. Now, there's kind of a few questions there. One, if the model does augmentation at the time of training, do I still need augmentation beforehand? What we call offline augmentation, whereas training augmentation is online at the time of training. And, generally, there's a few reasons why it can still be helpful. One is that you actually have a record of which augmentations happen on each individual image. So you could see and interpret and identify, you know what? My model is performing worst when my images are dark or when my images are horizontally flipped. And that would allow you to say, you know what? I should be collecting more data of that condition. And so if you do the augmentations before train time, you have that record and that system of record to be able to say that. And then a second thing that we see is, it's really easy to experiment empirically. And in most times, we actually see even a boosted performance when there's augmentations in the training pipeline and you still did offline augmentation. I think you have to be a little cautious of, depending on the domain problem you're working on, that you don't overfit actually to just the images that you've captured. And basically, the more variation there could be in the real world, maybe the more cautious you need to be with augmentation, because there's a lot more variety that you don't want to simulate. These are the only types of changes that can happen. But then there's also models, just as you said, that don't include augmentation at the time of training. And for these, having offline augmentation is immensely valuable, because you could write augmentations in PyTorch or TensorFlow or even DarkNet in your own specific framework. But then let's say that you want to try a model that was released in a different framework. You'd either have to rewrite your entire code for your augmentation preprocessing pipeline, not even sure that those augmentations are implemented the same way between those open source frameworks. But even if they were, you'd still have to basically redo this work that's not essential to the problem that you're working on. So having augmentation be independent of the actual training process can be beneficial for versioning your data sets and for having reproducibility and for reducing the amount of work that you're doing that's otherwise kind of redundant. Something that we work on at Roboflow really carefully and deliberately is maximizing the way the model can learn from a given augmentation. In other words, an augmentation could be implemented in a lot of different ways, or the way you order them could result in different quality models. And so there needs to be a lot of thought put into what should be the order of these augmentations that best maximizes the value of my input images. And so we make that be our problem so that the users can just be like, okay, I have confidence that when I select these augmentations, it's going to be intelligent. That actually kind of begs the question of, so we've been talking a lot about augmentation. And that's one of the types of ways we manipulate our images. But we should also mention augmentation's relationship to preprocessing, because preprocessing is also messing with my images. Could you break down what preprocessing is and how it differs from augmentation?
Actually, that's a common question that we get because it's a little bit unique to this sort of computer vision domain of having these different types of transformations that you're applying to your data. So the difference really is that the purpose of augmentations, as we touched on earlier, is to expand the amount of images that you're training on. It's to expand your data set to have more variety in the training data to prevent overfitting. And so because of that, the only images that you're going to apply augmentations to, except for in some special advanced cases of some new research, are on your training set. So you're not going to touch your validation or your testing set. By contrast, pre-processing steps, which would be things like resizing all of your images to a constant size and aspect ratio, or discarding all of the color data and saying, we don't care about color. Color's not important to this domain. We're going to turn everything to grayscale. Or even doing things like doing class management of like saying, hey, I labeled all these chess pieces on this board, but actually I don't care which ones are the rooks and which ones are the queens and which ones are the pawns for this model. I just want to train a piece detector. All of these things are things that you need to apply not just to your training images, but also to your validation and testing images. And so that's the real difference. And kind of the reason that you need to do that is because pre-processing steps are also things that you're going to need to do at inference time. So once you have a trained model that you deploy into the wild, your model is trained to recognize input data that's coming in a specific format. And so if you've turned all of your training images grayscale, you can't expect to feed color images to that trained model and have it know what to do with it. In fact, oftentimes it won't even work because the input size and the number of channels won't match the model. And so with the pre-processing steps, you need to apply those at runtime as well. And so again, to reiterate, the difference is augmentations are applied only to the the training set. And pre-processing steps are applied to all images, train, valid, and test, and at inference time.
So it's almost like pre-processing is more rule-based, and augmentation is a bit more randomly applies to each of the given data. Cool. I think that's a good summary. I mean, any other sort of parting thoughts that come to mind as we provide insight into effectively using augmentation?
Yeah, I think there's a reason that we have dozens of blog posts about this. It's a really valuable technique, and in this short video we weren't able to cover all the different types of augmentations, even not all the ones that we can apply inside of Roboflow. So we have other ones like Mosaic, which is a new augmentation that has shown really great results on improving model performance, or bounding box only augmentations where in that example of the cars, you'd be applying augmentations only on the car. Think about that hue change example of, the LA and New York color preferences on cars. You can imagine if you apply the hue transformation to the entire image, you're not just changing cars from green to red, but also the trees are all of a sudden going to be red, and that's not really what you want. I would encourage people to go out and read some of our literature on the augmentations and to learn more about this, because this is a great way to improve the performance of your models by enhancing your data set versus iterating on the actual machine learning model itself. And oftentimes that's where we see people get the most improvements on their models, is by pruning and curating and tuning and expanding their data set versus actually having to do novel research on the core machine learning aspects.
That's great. Well, thanks so much for tuning in to another Fireside Chat. Don't forget to like and subscribe to the Roboflow YouTube channel for additional tips, tricks, and announcements of things that we're up to. This is Brad and Joseph saying see you next time.